one is going to be pretty light on theory. It's going to be mainly practicing data structures. So sets and maps are like two of the most useful containers you'll need for competitive programming. So they'll be very helpful in like all of your future competitions. But first, there's a brief bit of theory that I'll go into. So there's two ways that they're usually implemented, the actual data structure. That is very hard to see on the board. But the first one is balanced trees. So I introduced binary trees last month. Balanced trees are basically an improved version of that. Because if you remember, with a binary tree, you can like search left and right by seeing if it's smaller or larger. But the main drawback is if you ignore, say like you ignore this left half of the tree, if you've just got this right one, it can essentially become one long linked list. And so then it's, instead of being log n, because you're splitting it in half each time, you have to search through the whole thing. Balanced trees basically fix that by making sure the tree is essentially balanced, which basically means the path on the left and the right are about the same length. There are a few ways that this is done. You'll learn about this in like second year data structures. It's not really important. The main thing is just it does it. It's implemented for you in basically every language already, so you don't need to worry about it, just to know that it kind of exists. So the most common way it's done, and the way it's done in the C++ standard libraries with red-black trees, just for demonstration purposes, I will try and go to this link. This is, I can't see what I'm doing, which makes it kind of hard. I should have made a clickable link, but if this works. Yeah, so basically if you insert different nodes into the tree, then it essentially keeps the tree balanced by doing applying a certain set of rules. Don't worry about the rules for now, but like if I do, I'll add some big numbers to the right so it keeps going down to the right path of the tree. And you'll see eventually if I add enough, it'll like fix it. So instead of being like really lopsided, it'll like rebalance it here. Yeah, so basically keeps it roughly the same length on each path on the left and right, so it's always log n. And that's the key point there. How do I get back into, yeah. So basically, since it keeps it balanced like that, inserting something to the tree is always log n, where n is your total number of nodes. Deleting something, also log n. Searching it, log n. Everything's basically log n. The other main way that sets and maps are implemented is with hash tables. So hashing is basically a way of mapping some arbitrary key to a specific index which you can put into an array. So a hash table, which you might have heard thrown around like the term before, it's basically just like a big array. This is not a big array, it's a small one, because I can't fit more than a lot on here for demonstration purposes. But essentially you have something called a hash function, which is some arbitrary function that takes a key. So in this case, I'm going to be using integers as keys, but a key can basically be whatever object you want. And it converts it to some usually big number. And it should be essentially random. And if you change the key even a little bit, so say the key is 5, if you change it to 6, it should completely change the output. So it essentially looks random, but it's always consistent. So putting the same key into the hash function always gives you the same output. The reason why you want that is then that number, you can basically take the remainder with however big your table is, and that gives you an index. So you have an index where you can look it up in constant time. So insertion, deletion, searching, all constant time. I put an asterisk there. It's not always the case. Can anyone, except any of the third year students over there, think of an example where it might not be constant time? Jason? Yeah, basically. So because it maps, the hash function essentially maps your number to an index, but if the index is already filled up, you have to look at the next free spot. And so if they're all filled up in a row, you have to like look through them all. And so especially if you've got a small table like this, when there's a lot of, it's called collisions, then it can take longer. But if you've got a big table, that's not really an issue. It just uses more memory. So tree over hashing, both of them like do similar things. They're used for looking up keys, essentially. Most of the time, you would use hash tables because it's faster. Like I said, it's usually of 1. The main times you might use a tree are when there's a good chance of collisions, when memory is more important, because for low collisions you need you need a big hash table with a lot of indices, essentially. And the other one is because trees are ordered, it's easy to iterate. So if you want to find what comes after 3, that's a lot easier to do in the tree, whereas within a hash table you just have to look up, essentially brute force, what comes next. There's no kind of notion of ordered values. Okay, so as an example, so if in this case object 1 is a key that I'm inserting to the hash table, so the hash function, f, just maps it to some big number. I take the remainder when dividing by 6, because that's how many slots I've got in my hash table. and I get 1. So that's where I put it. I've got a different key, object 2. I take the remainder after putting it through the hash function. That gives it index 0, so it goes there. Object 3 also has a remainder 0, and so then because that's filled, we got the next spot. That's also filled, so it gets inserted here. And so that's kind of the gist of how it works. This will come up more in like second year classes. For competitive programming, it's not really important because most of the time you just use abstracted containers in whatever language you're programming in, usually C++. And so that's where sets and maps come in. Sets are basically just a unique collection of values. So a set of integers is the most common one. So you've just got some arbitrary set of integers. So they can be implemented with either trees or hashing, and that's where that'll affect the time complexity of the operations. But they do the same functions, mainly like inserting values, checking if something's in the set. You can remove items from a set. And then you've got 2 main implementations of this in C++. The first is your std set. This is implemented using a red-black tree, so that's your ordered set, essentially. An unordered set is implemented using a hash table. So most of the time, you would use an unordered set just because it's usually faster, but set is also useful if you need that like ordering of elements. And then if you like, it's similar to a vector where you can put in this angle brackets, you put in whatever type you want to store inside. So whatever type you want to use as keys, here it's just integers, but it could be whatever you want as a key, as long as it has a hash function. So not all data types in C++ have inbuilt hash functions. Stuff like integers do. The main drawback is that collections, so like say an array or a vector, doesn't have a built-in hash function, so you can't actually use one with an unordered set unless you either implement your own, which is a pain, and so that's another reason why you might use an ordered set, because then that just works. You don't need to worry about your own implementation of stuff. Maps are basically just sets of pairs of elements. So instead of having just a single element, now you've got one element which is a key and another one which is a value. And so it's the exact same kind of thing here where you've got map and unordered map, which is essentially the same as a set and unordered set, but now you pass in 2 types. K is your key, so that would be an integer in this case, and T is your type that you're storing, which would be a string in this case. And so it works the exact same way where you've got, in this case, this would be a hash implementation of it, where you've got your keys, which are mapped to specific indices, and then your values are also stored along there. They're always implemented with both pairs of values stored, not just the second one, because of the collision thing. So like if, say, 9, after putting it through the hash function, if it got mapped to index 0, then you need some way to check that this isn't the key 9, it's the key 0, so we have to look at the next spot, etc., etc. And so that's kind of all the theory. So the rest of the workshop is just going to be basically practicing this in hopefully C++, but you can use Python if you'd like. So I've got, I think, 3 examples here, which I will go through first as examples, and then I've got, I think, 4 questions to try on your own. So all of these are on LeetCode, which is, so Code Forces is generally better for competitive programming type problems, but if you just want to practice like data structures, LeetCode's really good for that, so I'd suggest making an account. So you can follow along with this and have a go as well if you want, but I'll walk through the first few of these. So this LeetCode question contains duplicate. Given an integer array, return true if any value appears at least twice in the array, and false if every element is distinct. So basically, we want to see, are there any repeat numbers in the array? The easiest way to do this is, like I said, so sets always store unique values. So one way you can easily check if there are duplicates in the array is you iterate through the array, check every number and add it to a set. And each time you look at the next number, if you check or if it's already in the set. If it's in the set, then you've got a duplicate, so you can return true. If it's not in the set, you can add it to the set and keep going. So that's basically what this does. So we've got, this is our input vector. We're returning a Boolean. So I've created an unordered set, just called it st for set, because I don't want to, if I called it set, that would like overload with the actual set data structure. So it's good not to have naming collisions like that. So that's why I called it set without the E. But yeah, they're basically iterating through every integer inside that array. There are a few ways to check if something exists in a set in C++. I like using the .count, which returns how many times an element occurs in a set, which can only be once because they're all unique. So it basically returns 1, which is the same as true if it's in there, and 0 or false if it's not. You do also have things called multi-sets and multi-maps in C++, but you basically never need them. But they do have a slightly different way of implementing count because you can have more than one object. So basically, go through every element, check if it's in the set. If it's in the set, you've got a duplicate, so you can return true immediately. If it's not in the set, then we add it to the set. And if we get through the entire for loop, we've gone checked all of these numbers, none of them have been duplicates, we can just return false. There is also a slightly more compact but a bit more complex way of doing this, which is so unordered set. This is using a special constructor for that, where it basically looks at nums and puts every number inside nums into this set. And so nums.begin and nums.end, that's the same like syntax we used for sorting a few weeks ago. They're called iterators. I won't go into too much detail because you don't usually need them too often. But basically, if you look on like CPP reference, this is a way of just basically creating a new set with all of the values of another container. In this case, all the values inside nums. And so I'm checking the size of that set. If it's equal to the size of nums, that means every element must be unique. But if there are any duplicates, because the set only contains unique values, then it'll have a smaller size. Does that make sense to everyone? No? No? So if we think about, like, say you've got nums has 1, 2, 3, 4, 5. All this code is doing here is basically adding it all to a set. So if we start off with nums 1, 2, 3, 4, 5, we have a set which also has 1, 2, 3, 4, 5. So both of them will have length 5. Then they are equal, so this will return false, which is what we want because there are no duplicates. If, say, it was 1, 2, 3, 4, 4, then it's still length 5, but the set is only going to have 1, 2, 3, 4 because there are no duplicates in the set. That's all unique values. So then the sizes are different.
I get the syntax.
The syntax, so basically, I did it on one line just to make it compact, but it'll be a bit more readable if you spread it out. But basically, so unordered set to the end of this bracket here, that's essentially just creating a new set.
Oh, got it.
Then we're doing dot size on the set. Yeah. Cool. Does that make sense? Cool. Next one, ransom note. So we've got two strings, ransom note and magazine, and it's asking to return true if you can construct ransom note from the letters in the magazine and false otherwise, only using each letter at most once. So like you're cutting them out of a magazine and using them to put together a ransom note, essentially. So this one, the examples are a bit more helpful. It's not as straightforward a problem, but basically, first one's false because there is no A in the magazine. Second one is false because you need two A's, but there's only one A. And the last one's true because there are two A's, which you can use to construct the ransom note. And so this one is basically, you want to know, are there enough of each character in magazine to be used in the ransom note? So essentially this boils down to counting how many of each character occur in both strings, because we need to make sure there's at least the same amount of characters that are in ransom note inside magazine. And so we can do that with an unordered map, which in this case I'm using characters as the key and integers, which is the count, as the value. So I'm basically mapping each character to the number of times it appears. So I've got two maps, one for the ransom note, one for the magazine. Then I'm iterating through each character in the string and then adding it, so note map with the brackets, so it's the same like notation as like an array, where I'm accessing that key, that index essentially, and I'm incrementing it by 1. So this is just counting the characters in each of the strings. Then the next part, I'm looping through so this is looping through like the pairs, so C is the key, which is the character, count is the value. So I'm looping through each key and value pair in the note map. And so then for basically, this is looking through every character that exists inside the note. We need to make sure there are enough characters in the magazine. And so that's here. So magazine map C, that returns, or that gives us how many of that character appear in the magazine. If it's less than the count that are needed for the note, then we don't have enough characters, so return false. If we get through the entire note and we haven't found that issue, then it's possible, so we can return true. Does that make sense to everyone? Yep. There is also another simpler way of doing this one, just because of the restriction here. So there's a small constraint that all of the characters are lowercase English letters. So instead of a map, technically you can just use an array because there's only 26 characters that are possible. And so then you just do this, which basically subtracts the ASCII value of A. So then lowercase a essentially gets turned into 0 and Z would be turned into 25. So you use them as indices in an array. So that's kind of a more space efficient way, but is only possible because of this constraint. If it was just arbitrary characters, you'd need this map so that you could have any character just going to any integer. Yes, Jason?
What does the little C hyphen do?
With the C hyphen? Yeah. Yes, that's just subtracting it. So C is your character, which in C++ represents like the ASCII number. And so then A is also, because I've got single quotes, it's interpreted as the ASCII number as well. And so if the C is to the character A, then you're getting A subtract A, which is equal to 0. and so that gives you the first index. And then if you do Z, because each of the ASCII codes are like one at a time for the lowercase letters, then you get Z take A, which would be 25. And so this is essentially just converting each character to an index from 0 to 25. That's kind of like a space-efficient solution. It's definitely not needed. The first one's probably the most intuitive way of doing it, where you're mapping each character.
You have to use like 3 loops.
3 loops. 3 loops is the easiest way to do it. I'm sure there are ways you could do it with less loops, but especially in competitive programming, if something works, just do it. we don't really care how efficient it is, as long as it's efficient enough to pass the test cases, right? But yeah, it could be a cool problem to try on your own to see if you can make it in less loops.
Is it so C is a value in the first one, but it's indexed in the second one?
Yeah, also in both of these cases, C is a character, which in the first one, we're using a character directly as the key.
Yeah.
But in the second one, because it's a vector, which only has like integer indices, we need to map it from numbers like 0 to 25. But in both cases, C is like of the data type character.
Okay.
It's just one of the funny things about C++ is a character is actually an integer type. It's just from 0 to 255 instead of 0 to how big an integer can store. It's basically like a really small integer, because it's only used for ASCII codes, most of the time at least. Before I move on, were there any other questions about that one? No? All right. This one's a bit of a trickier one, unique occurrences. So given an array of integers, return true if the number of occurrences of each value in the array is unique or false otherwise. So this one's a bit more of a convoluted statement, but basically we've got some array. If we count the number of times each number occurs, so like 1 occurs 3 times, 2 occurs 2 times, and 3 occurs once, we don't care about the numbers themselves, but the number of times that each one occurs, so in this case that's 3, 2, and 1, are they all unique? So in this case, yes, they are unique, so we return true. In this case, 1 and 2 both occur exactly once, and so because that's the same amount of times, that's false. In this one we got true. I won't bother counting it out, but I assume each number occurs a different number of times to every other number. Does that make sense? Yeah. And so this kind of we can combine this almost using one map and one set, like the 2 previous questions together. So first, I've got an unordered map of integers to integers. So this is counting the occurrence of each integer. So for every integer in the array, we just increment the value of counts at that index or at that integer as the key. So this is counting up, basically mapping each integer to the number of times it occurs. Then the next part, we use a set and do the same thing that we did with the previous question, basically, where we iterate through every key value pair in that counts array. So value is the number that was in the array originally, and frequency is the number of times it occurred. So if that frequency has occurred before, then that's like a duplicate number of times, so we return false. If it hasn't occurred before, then we add it to that set. And if we get through all of them, then we can return true. Are there any questions about that one? No, cool. So those are some examples. I've got some practice ones. So I've got 3 easy questions and 2 mediums, if you do well there. I don't expect everyone to finish all of these. These are just to have a go at and maybe try it throughout the rest of the week before it's the competition on Saturday. But yeah, have a go. These are roughly arranged in order of difficulty. So start with the easy one. We'll start at the top and work your way down, essentially. It is on Discord, yes. The slides are on Discord. You don't need to type out the links. You can if you want. If you just search up like this bit here, like if you search LeetCode third maximum number, it'll come up. But yeah, that's basically it for the content part of this workshop. The rest of it, just have a go. Community and I and third years will be floating around and can help you. So cool.